Not all acids and bases are created equal. And one way we can distinguish acids and bases is by their strength. Now, I want to point out that strength does not equal concentration. Okay, so concentration tells us how much of a solute we have in the solution, and acids of varying strength may have the same concentration. So don't interpret that strength means that something is concentrated. So those two words don't mean the same. And so we want to think about that as we're beginning to understand what strength means, that it does not mean the same as concentration. All right, so let's look at the word strong. And so here on the slide, I have strong acid and strong base. And let's look at the definition so we can decide, what does that word strong mean? So a strong acid, if you read it, it says readily donates a proton. 100% of the acid dissociates into ions when dissolved in water. Okay, a strong base readily accepts a proton. 100% of the base dissociates into ions when it is dissolved in water. So this word strong that we see here, strong, is really talking about how much of the acid or the base dissociates into water. And so we're talking about 100% of the acid or 100% of the base. So these are acids and bases that when you put them in water, they completely go to form the ions, and that's what strong means. So they make a lot of ions. Now, some common strong acids I have listed in red: hydrochloric acid, hydrobromic, hydroiodic, sulfuric acid, nitric acid, perchloric acid. Those are all strong acids. And then the list of strong bases includes, it's not limited to, but all of the alkali metals and some of the alkaline earth metals, hydroxides. So these are the list of strong acids and strong bases. And if you were to have to go further in chemistry, what you do is you memorize these limited lists of acids and bases that 100% dissociate when they're in water. And if you're not on this list, then you're going to see you're defined as something that's called a weak acid or base. So the word strong means that you have 100% of that acid or base dissociated in water. For acids, they are readily giving away their protons, and the strong bases are readily accepting those protons. Now, for those of you in the introductory course, as we kind of survey some of this information and understand the basic concepts, you do not have to memorize these. But those of you going further may consider it useful to already start memorizing some of these strong acids and strong bases. Okay, so that's strong, 100% dissociation. So now let's look at weak. So weak acids, so now here's the word weak. There's a weak acid and a weak base. And let's look at the definition. Weak acids less readily donate your proton, and only a small fraction of it dissociates into ions. And weak bases less readily accepts a proton, only a small fraction of the base dissociates into ions. So these acids and bases don't go completely to make their ions. Now, one way this could be indicated when you see reactions, this might be indicated by a reversible reaction by the back and forth arrows, which when there's back and forth arrows, that kind of implies that we're not going to get 100%, where the strong acids, generally when we put those in water, we would have only one forward arrow because it's telling us 100%. So 100%, and then a weak is only a partial dissociation. Now, we did a lab where we investigated electrolytes, and if you remember, electrolytes are substances that conduct electricity in a solution because they have ions. You might also recall that hydrochloric acid gave a bright, bright light. Well, hydrochloric acid is a strong acid, which it means it dissociates 100% to form the ions. So there's lots of ions there. Bright, bright light on our little electrical apparatus. Where acetic acid, if you remember, it only let the filament, the little wire, glowed, which tells us there's not as many ions. Well, acetic acid is a weak acid. So acids and bases are electrolytes because they form ions, but some of them are what we call strong electrolytes because they form lots of ions, or weak electrolytes because they don't form as many. So that's a connection back to the previous chapter when we were talking about electrolytes and acids and bases being electrolytes. Now the relationship, so we know from the previous lesson in this chapter that when an acid donates its proton, the product it forms is called a conjugate base. And when a base accepts a proton, the product it forms is called a conjugate acid. And those are what we call conjugate acid-base pairs. Well, the relationship between the acid and the product it forms, or the base and the product it forms, is an inverse one when we talk about strength. So inverse means opposite. So what we know is here, the stronger the acid, then what it forms is going to be weaker. The weaker its conjugate base. And the stronger the base, the weaker its conjugate acid. So it's an inverse relationship. And here's a table from your textbook that shows this. So if you notice on this side, the arrow is pointing up and it says it's increasing. So this right here, these would be the strongest on the top. And as you go down, we get the weakest. And if you look on the other side, the arrow of this chart, the arrow is pointing down, and it says increasing, which means here we have the strongest, and here up here we have the weakest. So this is just a table that helps maybe illustrate what this was saying on this page. So on the acid side, you'll notice that when you have the strongest on the top, its conjugate base is the weakest. So it's an inverse relationship. The stronger the acid, the weaker its partner is, the conjugate base. And the weaker the acid is, then the stronger its conjugate base is. So it's an inverse relationship. Now we can use this relationship to help us predict equilibrium in an acid-base reaction. So here is an acid-base reaction, and where it says using acid strength to predict the direction of the equilibrium. And remember, when we talk about equilibrium, we're talking about are there more reactants formed in this relationship? Are there more products? Or sometimes there could be a substantial amount of both. But equilibrium, recall, means that the rate of the reaction, the forward reaction and the reverse reaction are equal. And so when we have this reaction, when that occurs, we often have where one side of the reaction, the reactants, or the other side, the products, are favored. And so in an acid-base reaction, we can use acid strength to figure that out. So the first thing I would want to do is find the acid and the conjugate acid, and we're going to compare their strength. So let's label, and we can just use this as a practice. So I see one partner, the one partners are here, and then I see my other partners, if I follow the C, are here. Okay, so let's label these as acids and bases. So if I look at this first one, H3PO4 here, and then I look at what it forms, I see that it donated a hydrogen. So this is going to be my acid, And then this is going to be the conjugate base that it forms. Now automatically this is Cn minus is going to have to be my base, but let's look. So here we have a Cn minus, and if I look over here, it's added, it accepted an H. So this base must have accepted the H. That would make this the conjugate acid. So that's just labeling the reaction. And if you want this in steps, if you look at the notes provided in the class, I have it broken down into steps. Okay, so written down step 1, step 2, step 3. So if we look here, how we figure out where the equilibrium is we find the acids on both sides of the reaction. So here's one. That's on my reactant side. And then I'm going to look at the conjugate acid on my product because I have to compare acids to acids. Okay, acid to acid comparison. Now then I would use this table, and the table will be given to you, and here is the side I'm looking at. I'm not going to look at this side because I'm comparing acids. I'm not comparing bases, I'm comparing acids. And what I want to do is identify which side has the stronger acid. So I find H3PO4, here it is. There's that one. And then I find HCN right here. And so looking at this chart says as I go up, it gets stronger. So this guy is stronger. So this is a stronger acid. And then in this case, this is the weaker one. It's lower on the table. This is the weaker acid. And the rule is, because stronger, it really wants to react, the side that's favored is the weaker side of the reaction. So the weaker acid is on the favored side. So what I would say when the question, what is the direction of the equilibrium? This is the weaker of the two acids that we compared. So this equilibrium is on the product side. So that is the answer. So we use it, and we could say, so the equilibrium's on the product side, which would mean if we put these two chemicals, the two reactants together, that it would produce more products than it would have reactants there. So the equilibrium is on the product side. If you want to see more examples of this, if you look under class lessons, you can see some other examples worked out.